Hello everyone, welcome to my channel. In this video, I introduce a very important tool in mathematics in general and in applied maths in particular. It's called the Laplace Transform. Now, I'm not gonna go into so much detail as far as this concept is concerned. I just want to provide the definition of the Laplace Transform, the notation of the Laplace Transform, and show you how we determine the Laplace Transform of a constant function, and to be specific, the Laplace Transform of 1 as a function of time. Now, maybe just briefly, why is it important that we learn about the concept called the Laplace transform? It's because in applied maths, for example, in differential equations, some equations are very difficult to solve. So what we do is convert them into algebraic equations by using the Laplace transform. Then we're able to solve those equations using simple algebraic techniques. And then by taking what is known as the inverse Laplace transform, we're able to move back from the complex domain, S domain, to the time domain, and then are able to interpret the solutions. Now, what is the Laplace transform? Let's go into the definition now. We define the Laplace transform as a function which converts a given function of a real variable, usually time, to a function of a complex variable S. Now, I've already explained the importance of this. We want to convert complex differential equations into simple algebraic equations, so to speak, and we're able to solve them using algebraic techniques. And then we move back from the complex domain into time domain by using what we call the inverse Laplace transform, which I'm going to explain in the other videos coming up. But let's look at the notation. So we are using carry L as the Laplace transform operator, basically saying that we have a function of time as the input, and then by using this definition here, we're able to convert a function of time into a function of a complex variable S, basically saying that the Laplace transform of the function f of t is the integral from 0 up to infinity of e to the power minus st times f of t dt. Now that is the definition of the Laplace transform. So now I wanna, remember I told you that this is carry L. It's carry L, written like this, carry L. Basically, we are saying that it's the Laplace transform operator. All right, now I want to explain how we determine the Laplace transform of a constant function, specifically Laplace transform of 1. It's critical because that one is one of the 5 that we're going to have to derive, and then later, using the 5 results, we'll be able to solve many other equations by using those 5. But our first one is the Laplace transform of 1. So let's just capture the notation first of all. Remember the definition. The Laplace transform of the function f of t is equal to f of s, capital F of s, which is basically the integral from 0 up to infinity of e to the power minus st times f of t dt. That's the definition of the Laplace transform. And therefore, we can say the Laplace transform of 1 as a constant function will be equal to, remember, 1 now is taking the place of f of t. It must come here. So it will be the integral from 0 up to infinity of e to the power minus st times 1 dt, which simplifies to the integral from 0 up to infinity of e to the power minus st, basically dt. Now you notice that this is an improper integral. So the correct way to write it is to say that this is equal to the limit as x approaches infinity of the integral from 0 up to x e to the power minus st dt. This is the correct way to write improper integrals. Now we have to evaluate this. Now I'm going to ignore the limits for now and then come back, consider the limits. So here is what I'm going to say. I am going to say let u be equal to the power of e minus st, and therefore differentiating both sides with respect to time, you're going to have du dt you notice on the right hand side you just have minus s, because minus s is a constant. Derivative of t with respect to t is 1. 1 times minus s is minus s. Multiply by dt both sides, you're going to get du is equal to minus s dt. Divide by minus s both sides, you're going to get minus 1 over s, if you like. Du is equal to dt. Why is this important? Because we have dt over here, right? Let me take this to page 3. So basically now what I'm saying is, on page 3, what I'm saying now is, therefore, if we are talking about the integral of e to the power minus st dt, this must simplify to the integral of e to the power u, and watch this, minus 1 over s du, because that's what dt is, as you can see here. And minus 1 over s is a constant. I can take it out. Minus 1 over s times the integral of e to the power u du. Now you agree with me that the integral of e to the power u du is just e to the power u. So this is minus 1 over s e to the power u. But what is u? Coming back here, u is minus st. So this is going to be equal to minus 1 over s e to the power minus st. Fantastic. Now coming back here, so we now can consider the limits, because this integral has been evaluated, disregarding the units. The integral of e to the power minus st dt has been evaluated to this. So we're now going to say, therefore, the limit as x approaches infinity of the integral, I want to make sure that this is clearly seen here. Give me a minute. As x approaches infinity. Right, that's better. Of the integral from 0 up to x of e to the power minus st dt is just equal to the limit as x approaches infinity of what? Of this expression, minus 1 over s e to the power minus st. And remember, we're evaluating from 0 up to x. From 0 up to x. Now I'm moving to page 4, and I want to bring to your attention the fact that minus 1 over s is a constant, so it can be taken out. So we're going to take minus 1 over s out. Minus 1 over s times the limit as x approaches infinity of e to the power minus st evaluated from 0 up to x. Now I'm going to rewrite this by using laws of exponents. This is equal to minus 1 over s times the limit as x approaches infinity of, watch this, 1 over e to the power st. Remember, laws of exponents, evaluated from 0 up to x. Now, what does this mean? This means minus 1 over s times the limit as x approaches infinity of 1 over e to the power sx minus 1 over e to the power s times 0. Remember, you put x there and put 0 there and subtract. What does this simplify to? This simplifies to minus 1 over s times the limit as x approaches infinity of 1 over e to the power sx minus 1 over e power 0. Remember, s times 0 is 0. What is this? This is minus 1 over s times the limit as x approaches infinity of, I'm going to keep this one the way it is, 1 over e to the power sx minus 1 over 1, because e power 0 is 1. What does it simplify to? It simplifies to minus 1 over s times the limit as x approaches infinity of 1 over e to the power sx minus 1. Now, I want us to look at this expression here, because many students were telling me, please work on the Laplace transform, especially the limit part. We do not understand how it works. So now I wanna show you something here. I want us to look at this concept or this expression 1 over e to the power s x. Remember, s is a complex variable, a complex number. So let's assume we are looking at the real part only. Remember, a complex number can be written in the form of a plus bi, where the real part is a, the complex part is bi. Now ignore this for now. Let's focus on a. And I'm going to let, for example, for people to easily understand, I'm going to let a be equal to some number 2, for example. Then this would be simply written as 1 over e to the power 2x. Now I want to increase the value of x and see what happens to the whole of this expression. So now I'm going to say, what is this evaluated? What is 1 over e to the power 2x evaluated at x is equal to 1? The answer is going to be 1 over e to the power 2. 2 times 1 is 2. And what is this? This is equal to, I have a calculator with me here. So it's going to be 1 all over e to the power 2. The calculator says 0.135. I'm going to take 3 decimal places. 0, maybe 5 decimal places. 1, 3, 5, 3, 4. 1, 2, 3, 4. All right, the fifth digit must be rounded off to 4. Right. Now, what about if we increase the value of x? So 1 over e to the power 2x evaluated at x is equal to, let's say, 2. So we're changing that expression down there. This will be now, if you agree with me, 1 over e to the power 4, because 2 times 2 will be 4. What is this equal to? So we're changing that power now to 4. What we get is 0, 0, 1, 8, 3, 2, if I maintain 5 decimal places. The decimal system, the American decimal system, the comma, but you can use the dot there for a decimal place, a decimal point. For example, this would be written as 0.13534. You can also write this one as 0.01832. Now I want to increase the value of x to 5. What if we are saying 1 over e power 2x evaluated at x equals 5? What should this be equal to? We're just changing. So 5 times 2, it will be 10. So it will be e to the power 1 over e to the power 10. What is the answer? Watch what happens there now. 0 point all comma 0, 0, 0, 0, 4 zeros, and the last digit, if you round out 5 decimal places, it's going to be 5. Now watch what happens here. When x increases, remember 1, 2, 5. When the value of x is increasing, the value of the entire fraction decreases. That was the first value, second value, third value. So as x increases, the whole of that thing, this expression here of fraction approaches 0. So basically we can say that what we have here, as x approaches infinity, the whole of this fraction approaches 0. And so what we have in there is just going to be 0 minus 1. So let's complete this on page 5. So we're saying basically, this is page 5. So we're saying basically that expression, put these papers together. I'm taking my time here. I want you to make sure you understand what's going on here. So this is going to be minus 1 over s times the limit. And we said limit, we're taking the limit already there now. So we're just going to say times 0 minus 1. And what does this simplify to? This is minus 1 over s times minus 1. And you agree with me that this is just 1 over s. But then again, we must understand that this is true because the assumption is s is greater than 0. So we can now conclude, therefore, and I'm going to explain briefly about why I'm saying s must be greater than 0. if you come back here, the reason why this works is when x is greater than 0 and s approaches infinity, the power is positive, and therefore the whole fraction decomposes or converges to 0. So therefore we are saying the Laplace transform of 1 is actually 1 over s. The assumption is s is positive or greater than 0. So this is one of the 5 very critical results we're going to derive by using the Laplace transform, and then from the 5 we'll be able to answer almost every question, be able to deal with most of the differential equations that would not be easily solved by using simple elementary methods. All right, I hope you found that useful. Tell me what you think about this. Definitely I'll be coming back with many more videos on this. This is just the first one. Many more are coming on this, and we will look at applications when it comes to solving of differential equations. All right, I'll stop there. See you next time.